So an important assumption that we made about every single one of our fluids is that they are incompressible, or at least as of right now. So what does this mean that they're incompressible? Well, of course, it means that the divergence over velocity vector is zero. So whatever comes in goes out. There's no change in density, for example. Not even changes in pressure cause the change in density. Why is it changes? Just saying what? In P do not cause uh, changes in density. So changes in pressures do not cause changes in density, and our assumptions are quite true for what fluids we uh, are using. It's pretty common, like for example, water is quite incompressible. You probably heard it before a lot. Um, that is incompressible, and we are using this assumption for gases as well. If the local Mach number is below 0.3. What is Mach number? Well, the Mach number is actually the flow speed. So what is the speed of the flow divided by the speed of the sound inside this uh, fluid. This fluid. This is the Mach number. We can say that they're incompressible for Mach number less than 0.3 because if they are pretty slow, then the air has time to readjust all around. So all the, for example, if you move your hand around in air, you can say that the air is not really compressing, you just take up the space that your hand was occupying before. It has time to go around. Now, if you're going very fast, then the air does not have time to uh, adjust itself, and so we need to start talking about compressing liquids. Um, Now, earlier we said that our divergence equals to zero. We can prove this with our continuity equation, and so we say that ui dx I is equal to zero. A better line over here. So here, of course, we say that it does not change over time because why would it change over time if there's nothing happening? And we just we're saying, of course, that the density also does not change with the uh, over space, and so this is a divergence. If this is equal to zero, then we have divergence. We have no divergence. So an incompressible velocity field is considered divergence free. Um, Now you can use this in the momentum equation as well, and it means that the pressure terms don't change. The pressure terms don't change, but we can simplify the viscous terms because, as you remember, in our d tau ij over dxj, so we have d or dxj, and then we plug in our tau values, so we have mu dui dxj plus duj over dxj minus 2 over 3 mu duk over dxk, and our current delta ij. So this one side is equals to 0 because that's just divergence. Um, and we just end up. Actually, you know what? I probably should do it. I should do it step by step. So this will go inside here, and we have our mu, which does not change based on our distance, so derivative does not get applied. We have d squared ui dxj. Uh, Let me write it twice. dxj plus d squared uj dxj dx I. This one also goes to 0. Um, Yeah, so we're just for the first one, which is just mu and the Laplacian of also this one because it's compressive again. Laplacian of our ui, and uh, this is what happens in our momentum equation. And it's much easier to deal with stuff like this. For example, also our once our density becomes a parameter, for example, when we end up doing our mu over rho, we end up saying kinematic viscosity, which is a nu. So we go from mu to a nu. Uh, so this becomes a parameter. Continuity momentum become a complete description of the flow. So we don't need really anything else. Our energy equation, momentum is no longer needed. Pressure becomes a Lagrange multiplier to enforce continuity. It does not apply to us at all. We can say, in fact, that our pressure is just a function of the velocity field. So our Laplacian of the pressure is equals to the negative rho. That's going to be just, I'm just going to put it in the short form. Negative rho du j dxi du du I dxj. Now you can expand this and get everything. And this is our pressure Poisson equation. Have this welcome.